Yeah, I was just saying thank you for the kind introduction, Kelsey, and then the invitation from US Clyber. Um, yeah, I will dive right into it. So my name is Jatan. I used to be a postdoc at Columbia, and the work that I'm going to present here on a stochastic machine learning model for wildfire activity in the Western US was work done at Columbia, and this was funded largely by the Ziegler Family Foundation. I'm no longer affiliated with Columbia, and I have this private affiliation, and so the views that I'm expressing here are just my own and not my employer's. Um, and and the research that I'll be presenting here was greatly enriched by working with several awesome collaborators. They're listed on the screen here. Yeah, I'm sure some of these are familiar to the US Clyber community. Um, okay, so fires present a rapidly growing challenge in a warming world, and this sort of thing came to head at first in 2020 when we were all locked in, and there weren't enough firefighters to go around, and that resulted in many more acres, besides having record-breaking temperatures and dryness. But the other sort of hinge point in terms of perception came in 2023 when Canada's record fire-breaking season burned about 18 million hectares. And I think of this as a focusing event because that created damage to both the human and natural ecosystems. And the smoke, the aerosol emissions from these fires traveled far and wide, not least to New York, where I'm currently based. And so the fires even though the fires that I'll be discussing in this talk are in the Western US, fires affect everyone, not just in the US, but also in continental Europe and further. So I think of this as a very illustrative example of how fires affect everyone. And also from a more of a modeling perspective, I think of this as like a new fire triangle. So traditionally, the fire triangle on the left here delineated fire behavior in both space and time, where as you go from seconds to days to decades in time, and microsites to wildfires to regions in space, you see the interaction between different elements. So for instance, at the lowest triangle here, it's the interaction between oxygen, heat, and fuel, which causes a flame. And then as we go to a wildfire scale, it's the interaction between weather, topography, and fuel that causes fire behavior, and then onwards to regions where you can see fire regimes that have lasted for decades to centuries, and these are the interactions between climate ignitions and vegetation. So in a meta framing sense, fire modeling is a very useful exercise because it sort of brings together the modeling community, the predictions community, and the observations community to create wildfire resilience and management. And so, some of the work that I'm presenting here hopefully contributes to that too. So the question in all machine learning talk sort of really boils down to, or at least one of the motivating questions boils down to, why machine learning in this case? What does machine learning bring here that we could not address with standard physical, climatological or statistical methods? And this is how I sort of think about the problem. So the data in this case that I'll be working with are fire locations and occurrences between 1984 and 2020 on monthly timescales. So these are the black dots on the left hand side, and these are organized across the Western U.S. in different regions, broadly speaking. So in the green, gray, and yellow are forests, plains, and deserts. So these are three broad classifications based on the primary vegetation in these areas. And in these tiny little boxes, you can also see the ecoregions. So these are EPA-defined ecoregions that are roughly climatically homogeneous and can be used as a way of understanding fire activity or in that region. It's also something historically that people have used as like an aggregate scale on how to understand fire behavior. And these also are a good way to understand the trends over the past few decades. So in these regions here, so in forests, deserts, and plains, you can see that in forests there's almost an exponential increase in the annual area burned in red, even though the frequency is more or less constant. Deserts and plains, on the other hand, are seeing a linear increase in the annual area burned. Um, and this is also sort of emphasized by this plot here, where you can see that it's not just forests that are burning. Sometimes fires that start in forests sort of bleed across in what is known as the wildland urban interface. And so the challenge really is, how do you summarily describe all these fires in these different regions, which have interactions between different elements of the fire triangle, without individually modeling each fire or individually modeling individual ecoregions. And so in this case, machine learning, you should think of this as a very smart way of doing a regression problem that captures the relationships between the different fire drivers in these different regions, all in sort of one model, and I'll sort of walk you through the details. Just to situate ourselves into what the data looks like, so I'll be focusing on the VUMI dataset that was introduced by my collaborators, and it's publicly available here. And this is basically a dataset with a spatial resolution of 12 kilometers by 12 kilometers and a temporal resolution of about a month. So you can assume that like a fire within this dataset has burned within a month. So even the largest fires typically burn about a month. Sometimes they go more, but we sort of constrain them to a particular month where it started burning. And the total grid cells in this data set are about 10 million grid cells, and the total fires are about 18,646. And just to sort of visualize what the fire looks like in this grid world, I'm showing two big fires in the data set. One is the August Complex fire, which burned about 1 million acres, and the Dixie fire, which burned about 500,000 acres on this grid. And so the challenge really becomes, how do we summarily describe all the weather conditions or the climate conditions that have existed in this grid cells, and all these grid cells that are overlapped by the fire, and use that to sort of train our machine learning model. And so this is clearly a simplification problem in a way, where we take total potential predictors to be about 51. And then I'll walk through these in a bit, with the same spatial resolution as the data set. And we create these effective input predictors by sort of averaging it for the fire sizes that are taken to be the average of inputs over all grid cells that are intersected by the fire's perimeter, weighed by the fraction of burned area. And so this basically creates an average sort of temperature or average weather profile or average climate profile that each individual fire is seeing. And this is, and the rough categorizations of the different kinds of fire predictors are four. So we consider climate and fire weather, we can vegetation, topography, and human-related variables. Climate and fire weather is further divided into hot, dry, indices, and others. So hot is, of course, high temperatures, or high minimum temperature. So this is Tmax, which is the maximum temperature, Tmin, which is the minimum temperature. We further, organize this by like consecutive months of high temperature, of high Tmax, consecutive days. So the superscript here indicates like a 3 or 5 or 7 day average of high Tmax and Tmin. So Tmin is just the minimum temperature of the day. Dryness is the most important predictor here, is vapor pressure deficit, which is a measure of the atmosphere's thirst. So it indicates how dry the atmosphere is. And again, similarly, we have these temporally lagging variables here for like the antecedent VPD across a few months. And so the idea here being that if it's been dry for the past few months, or n months, so here we consider rolling means of 2, 3, and 4 months, that means the vegetation and the grid cells that we're considering is drier as well. And the other variables are precipitation, anomalies, snow water equivalents, and so on. We also consider the standard fire weather indices, and then wind and lightning, because these are connected with fire spread. Vegetation is fairly standard. We consider forest, grassland, shrubland, biomass land fractions based on the natural land cover data set. Um, we also consider the mean precipitation in the previous 1 and 2 years, because that correlates in drier regions or semi-arid regions with fuel growth. So if it rains more in the previous year, that means there's more moisture available for vegetation to grow. Then there's the static variables, slope and southness, and then the human-related variables, which are number of campsites, distance from campsites, distance from roads, population density, and population density of areas greater than 10 kilometers square, and housing density. I'd also like to emphasize that humans play a mixed role with fires. So we, of course, set more fires because of our presence through campsites and other ways, but also we also put out more fires, right? So we take prompt action whenever the area within a certain region is close to a human settlement. So humans have this dual relationship with fires. And the idea is to statistically capture this. So what is the machine learning model that we are using for our as our model for the fires? And so here we have two models specifically. We use a mixture density network with a general loss function. So you should think of this as a feed forward neural network, which instead of predicting a scalar, so a single quantity, we predict the parameters of a distribution. In fact, the parameters of multiple modes of a distribution, and the only constraint that we impose is that these modes sum up to one. And so this is the mathematical formulation. And the two mixture density networks include one for the fire frequency and one for the fire sizes. The fire frequency, the form of the distribution that we model is something called the zero insulated Poisson process. So these are just the parameters of a Poisson distribution with some weighting to capture the fact that the data set that we're working with fires is in balance. So mostly we see fire presences, and the data set for any given year and month, in most cases we don't see a fire, right? So fires are rare. And similarly for fire sizes, we consider the generalized Pareto distribution and the log normal distribution, and we have to include a weight factor because fires sizes have a long tail where most fires are small, but the few fires which are the largest ones are the largest and contribute the most to the total burned area. And if you take anything away from this talk, it's basically that instead of creating these custom regression models for individual regions, what ML allows us to do is to distill these about 30,000 parameters for these different grid cells into about 1,000 parameters, because we are able to train this all in one box, so to speak. In terms of model training cross-validation, we do this traditional 70-30 split between using fires from 1984 to 2019, and this is randomized, so it doesn't have any temporal correlations, and these are broken down. The test data, and this is the most stringent test data that we use, is we just don't let the model see all fires in 2020. But of course, it also doesn't see fires in previous years as well. But the test data is something that we leave out aside. And then the leave on our cross validation is the validation. So the validation data set that we use, the 70-30 split. So the 30% of that, we do this leave 1 year out cross validation as well. So we average, we construct the validation accuracy by averaging all subsets of fires created by excluding the years that occurred in one contiguous year for each year in the study period. So we do this for all years between 84 and 2019. This is a separate cross-validation strategy. And we find that, even if we leave up to 3 years of data set, 3 years of data, of fire data out, there's only a marginal decline in the performance when doing so. And we measure these sort of metrics by this correlation and the chi-square statistic, and the details of which are provided in this table. So once the training is done and we ensure that the model is not overfitting, we use this to predict both the frequency and the sizes of fires. And we do this. I mean, I must emphasize this, that the model is not constructed for like any particular region. The model is constructed grid cell by grid cell. And we then sort of analyze the results cumulatively, because that allows for like a better comparison with the previous model, with the previous methods in the literature. So here I'm showing the cumulative Western US results for the monthly and annual frequency for fires. And you can see that in orange, so this is the left-hand plot, the modeled fire frequency with the uncertainty distribution in the bands. This is the 2 sigma uncertainty distribution, more or less captures the trend and the interannual variability of the observed fire frequency. And if you look at the similarly for the area burned, you see in the annual area burned case, again, it does very well across the decades, and the only time that it really fails is after 2020. So 2020 and 2021 were anomalous years, and I can say a little bit more about that later if there is time for why the model failed. And again, in the annual area burned, you see that here we show the 1 sigma uncertainty band, because this is a heavy tail distribution, and the mean is shown in the solid line. We also analyze the results by ecoregions. So these are sub-regions within the Western US map. So the map I showed in the first plot, these were the regions in the boxes. So these are some of the regions that I selected pretty much at random are Sierra Nevada, Pacific Northwest Mountains, Northern Great Plains, and the Intermountain Desert. So this is the Great Basin. And you see that the fire frequency results are pretty good across regions. So there's some spatial variation, and all of these, we analyze in detail in the paper. And the fire size is even better for these regions. And again, the fire size, or the total annual area burn, or the monthly area burn, to derive this, what we do is we first simulate the fire frequency with the fire frequency MDN, and then we use that to simulate the total fire size. So this is a doubly stochastic process in that sense. And as I said, like the most interesting thing that we found about 2020, because even in the plots that you see here, 2020 is something that especially say for regions in California and in the Pacific Northwest, the model really misses the large fires that were seen. And part of the question really is that is this a model failure, or is this really like an anomalous year as such? And to do this comparison, we compared the model results with previous extreme fire years, so between say 2012 and 2020. And then so what I'm showing in this plot are the annual area burn for 3 different scales. So for the Western US, forests, deserts, and plains. And the sort of striking result here is that even for previous extreme fire years, the model did actually pretty well. So the band that is shown, and so the red diamond is the observed annual area burn for these different regions, and you can see that in 2020, really the observed area burn was like pushing at the most extreme, at the extreme ends of the distribution. This was in the 99.5th percentile or something, which shows that actually, and if you break it down by regions, in fact, it's in the forests region. So it really was the case that in 2020, not just that there were more extreme fires, these were extreme fires in forests, in remote areas, when we could not send firefighters to extinguish the fires. And of course there were other complicated other complex occurrences there, like there were, for instance, in the August complex fire that I showed earlier, there were lightning clusters that were anomalous. So there are multiple strands to the story, but it definitely indicates that 2020 was an extreme fire year, that the model, like it was only in the 99.5th percentile of the model that we could model it, and the median was not a good representation of reality. I think I'm sort of hitting up on time, so I will just I'll just present the slide in very brief detail. But the idea is that this is not just a black box. We can also use something called the Shapley predictor importance. So these are like ways, through permutation to figure out which predictors of the fire predictors that we use contribute the most to each of these different models, the fire frequency and the fire size, mixture density network. And we find that vapor pressure deficit in both cases, in fire frequencies and fire size, is the most important predictor. And if you see here on the rightmost side, we are also able to recover what we know are physical relationships with fire. So, for instance, other works have shown that VPD and fire sizes have like a quasi-exponential relationship, and we were able to recover this even though we were training across a very large data set of individual grid cells, and that to me was like a very encouraging sign that machine learning models actually are able to learn these physical relationships as long as you bake in the right sort of inductive biases. And then we are also able to calculate the predictors by ecoregions, and more or less this tracks with previous results in the literature. I'll skip this because this is like a further like we built upon this smell fire work by combining this with a seasonal with seasonal weather forecasts, and the idea was to push this to sub-seasonal to seasonal scales. I'm happy to chat more about that. But I'll just leave my summary slide here, and I want to leave some time for questions. Thank you.
Yeah, thanks for this, Jatan. This is really interesting. I was actually wondering a little bit about on your summary when you talk about predicting at the S2S timescale, a lot of the predictors that you include may not necessarily be standard outputs from these S2S models. So I was interested in how you approach that problem and what implications you think that has for being able to predict these sorts of quantities of the fire or dimensions of the fire.
Yeah, that's exactly. Yeah, you get into the heart of the problem, Weston, and I'm sure, of course, familiar with your work. So you're exactly right. So it turns out that these. So I was relying on the ECMWF system, the CES5, just primarily because it was easier to access. I know NOAA and NCEP have their own system, but you're right. Like only a subset of variables are actually predicted by the seasonal ensemble. And it turns out that yes, so the performance does suffer, but it turns out that because the uncertainty in these forecasts at these scales is fairly large, there's some level of arbitrage you can do in terms of like basically like it depends on what you're interested in. So if the idea is to get like really accurate forecasts for what happens in some zip code in the Western US, you're out of luck. But if the idea is to do some preparedness on regional scale, so then it's sort of like changing the framing to like a decision theoretic framework. Like what is the most useful information you can get given this degree of uncertainty, and sort of using that as a lens, rather than like focusing on like the accuracy that will of course not be the case as you see when you're working with historical data. So I think I'm basically agreeing with you that this is actually important, and so my recommendation here is that you sort of use the uncertainty, like the uncertainty here is your friend, and you can sort of frame your decisions that way rather than like trying to get the accuracy that you see with historical data sets. Yeah.
Okay, up next we have Maria.
Hello, can you hear me?
Yeah.
Thank you so much for an interesting talk. That was excellent. I was curious about some of the nuance in the methodology where you describe the cross-validation approach and then you show results over a time series. I think this is slide 10, where you're showing results from like 1984. are these results before 2020 validation results from the cross one, the levo and out, or are these results of the training set? Yeah, and just for some background, we've been talking about like the standards around how to show results and limitations and assumptions. So anyway, yeah.
Yeah. So no, this is a very good question. Thanks for that. So in this case, so the results that I'm showing here, the leave one out here in this case was actually 2020. So there was no fire data included for 2020. Actually, also for 2021 and 2022. But the data that is shown from 1984 onwards, this was done in the 70-30 split. And so what I'm showing here includes part of the training data. So that is one thing. But the second thing, where I think this is still a fair result to show, and it's not overfitting, is that the training data was randomized. So this is not where we did, okay, 84 to 2008 is the 70%, 2008 to 2020 is 30%. We'll just keep the temporal correlations as is. No, we actually completely randomized the data set, and so and it didn't see consecutive months or years, and so yeah, I think that was the sort of compromise that we ended up going with. But I think I don't think this is like the final word on the topic on how you how do you deal with standardization of certain training and validation practices. But this is just what we did.
Okay, great. I'll let the others ask questions. I see other hands. Thank you.
All right, next is Kelsey.
Yeah, thanks for the talk. My question's about, so you trained the model with historical observations and it was on a monthly timescale, I believe. Do
Yes.
you have a sense on whether the observational data set is long enough to account for like all of the relevant meteorology at play for these kinds of events? Is that like a concern of yours and how you might maybe want to approach that? And if you don't think that maybe we have a good sense of like if it's a long enough observation set or what?
Maybe I think I know where you're going, but if I can ask a clarifying follow-up. When you say long enough, are you thinking really for like S2S or like seasonal? Like, have we seen enough ENSOs? Is that the
Yeah, I'm kind of thinking more on the S2S timescale, seasonal timescale, just in the sense of this is they're pretty rare in general, wildfires. So considering how rare they are and how like they're pretty random too, like do you think that our observation, like it's only from 1984 to 2020? Do you think we need more samples? Essentially, that's the question. Yeah.
Yeah. No. No. Okay. So I see where you're coming from. So I'll say two things, and this is more of an opinion, and probably there's since this is an open conversation, I'll say this. So I think there's the way I've sort of come around to this is there's a difference in philosophies in terms of like how we analyze climate data, and then like an extreme event data that is like downstream of that climate data, right? So fires, for instance, of course, they have this interannual variability, they have some seasonal variation and so on, but as such, it's a local event, right? So given I can sort of toggle the climate, I can toggle the weather, but the ingredients for what constitutes a fire are fairly local, right? So if you have enough, if it's hot enough, it's dry enough, it's and you have the right conditions, there will be a fire, and provided there's ignitions. So the trickiest part in modeling fires, to actually answer your question, is to get the ignitions right. And if you want to project this into the future, I mean, you will be constrained by how well your climate and then medium range weather models do. So that's not so much a question about the fire model. It's really a question about your climate and weather models, right? So you should think of this model as something that takes you from any given set of inputs to like the fire activity, and it doesn't sort of like it's a good thing that it's able to capture the trends. So it was we were the strengths of this model were that we were at an aggregate scale getting the number of fires and the annual area burn or like the monthly area burned right, but it wasn't so much a case that we were doing the full climate modeling. No, no, no. This is actually a much simpler model in that sense. But in terms of having more data, or like even as a validation test, and then this has been suggested to me several times, is to sort of use one of these models and try to plop it in a different part of the world, not completely different. So you want to be like in, you can pick like a which is something similar to the Western US. So some examples were like Australia, for instance, or Southern Europe, which has now been seeing more fires. So perhaps there could be a way of like even getting more samples for this kind of model by expanding the domain, so to speak. But otherwise, you're not limited by data as such. You're limited by, the randomness of actually where fires occur. Yeah, sorry, that was a bit of a long-winded answer.
Okay, thank you.
All right, next we have John.
Hi, it's a nice talk. Maybe I missed this. When you're leaving out data for training, how you said it's randomized, and so that helps not overfit. Were you leaving out months, years? What's the leave out sample size?
Yeah, so and we did this. Yeah, sorry, I was not clear earlier. So in this case, okay, so the process goes like this. You in this case in the first sort of 2 points here, I'm illustrating that we take all the data between 84 and 2020. We just leave out 2020. We don't consider it. And we take the remaining years between 84 and 29 and then do this 70-30 split in a way where, the split is random in some sense. So we choose a random subset of 70% of the data from this pool, and 30% is the validation.
Yeah, that's what I'm trying to understand is I get that part, but did you leave out 70% of the years as a whole chunk, or did you take randomize 70% of the data? So
the latter.
There's a lot of autocorrelation in the data though, right? And if you randomly leave that out, so for example, if I take 1998, so ENSO year, super predictable in the winter, and I leave out 70% of those days, 30% of those days tell me a ton about the 70% of those days that go into the training. Tell me a ton about the 30% that I left out that I am assuming is independent, but are definitely not. So you're actually, that's what I'm saying, especially on these long time scales, there's a ton of autocorrelation, and randomly leaving it out is not, that's not IID data.
This is true. It is not IID. The only thing I will, I see your point. The only thing I will say, well, I'll say two things. One was, just in terms of like explaining what's on the slide. So this was the configuration that we actually used for showing the results in the slides that followed. And then we also did to calculate this score, the leave one out cross-validation, and these scores are different models. What we did is we repeated this procedure by leaving out one of these years. So instead of leaving out just 2020, we then did it for all years from 84, 85, and so on. And then to calculate this leave one out cross-validation score. So we repeated this process instead of 2020 by doing all these years so we created about 40 subsets, and then this is the mean of that. And then we also another test that we did was, okay, how many years can we just leave out, like consecutively, that is, and still see reasonable performance? So that's when we left out, say, I remember one of the tests we did was we left out, I mean, actually, I can show this here. So we left out this 92 to 95, so to get some of these spikes out. And it's only after 3 years that, you know, we saw that actually, yeah, the performance sort of decayed. But to your point, which I think, so that was one point, just in terms of like, you know, making this clear. But to your second point about autocorrelation, I'm of the opinion that, yeah, so for instance, yeah, if we look at 98, the way this split works is that it doesn't have any sort of information that it is 98, right? So there is no, everything that is encoded will probably be in say the temperature, like, okay, sure, there's this dipole over the Western US, and so it kind of knows. Sure, that could be the case, but I think, yeah, I never really interrogated, and then perhaps this is really a I'm not sure if you're saying this, but perhaps you're right. Like, even with these trained models, one can do more science and sort of ask, like, okay, from a fire science perspective, is this a representative sample of the training data set, or am I still, like, you know, overfitting? I never really analyzed what the 70-30 split was randomly doing. To be fair.
Yeah, no, I think that's really nice explanation. I like the additional leave out one out. I think being more strict is always good. I mean, I think that my initial reaction to that is, you know, you leave out 3 years and it starts to, you know, performance starts to degrade. Then the question is, the obvious follow-up question to that is that because of what Kelsey mentioned, which is that you are more data limited than you think, in which case that's why the score is going down, or it's because you have way more data leakage than you think you do, and by the time you get out to 3 years, you are starting to be strict enough that you're not actually including information in your training that's giving you skill. And I think that the reason why I mentioned the autocorrelation is I know that like if you take a package like a canned, I don't know what packages, you know, what your code practices are for writing your own, you know, what amount of your code is canned and what's not. But, you know, like a lot of this canned routines do the randomized thing where it takes out, you know, 10% of the data and it does it randomly depending on your problem, right? So for example, in a coastal problem, I know I've done this with trying to predict coastal flooding. A lot of memory in there. There's a lot of monthly memory, right? And if you do it in that canned way, you can get miraculous scores, even though you're presumably being quite strict on the cross-validation. And then if you leave out in chunks instead, where you enforce, you say, well, I'm gonna do it in a block fashion, and I'm gonna leave out 4 years, and then train on the rest, and then do it, your skill drops off wildly. And the takeaway there, right, is you really have to pay attention to where the memory is entering into the problem. I think that would be my only comment.
Thank you.
Yeah.
Let's take one more quick one, and then we'll have to go on to the rest for the panel business.
And the last one is Mary Beth.
Okay, quickly, thank you so much for the talk. A quick comment on what John had said, and you mentioned at the end is the blocked. So like basically blocking the time series into chunks and then using that as test data has been a way that I've used to help combat like data limited. I know it's like really challenging, especially with the autocorrelation. So basically doing like a chunked cross correlation could help. I just had a question about your idea about applying to a different area. I liked your comment about the emissions being a critical factor in this, more so than like the weather and climate. And so I'm just wondering how you would verify that, say, Australia has similar emissions to California to be able to take this model and use it there in terms of like that underlying emissions?
I mean, maybe just as a follow up. So yeah, so the idea. So I'm not predicting emissions in this data set. It's just fire frequency and sizes. The emissions was like only motivation because I mean, that's how it, one of the immediate ways it impacts us. So maybe if I can ask you to clarify, like, what do you mean by emissions data set in California and Australia?
Just like how you would determine if two places are similar enough that you could use one model for another place.
Yeah. So I mean, I think the machine learning or statistical answer is that you look at similarity scores in terms of you do some clustering to see if these and of course you want to normalize these by some climatology and see that if the variability in both these if the climatology and the variability in both these two regions are similar, you can create a score and see if it passes a certain threshold, then you see that these are you can more or less apply this, say, within distribution, and it's not out of distribution. I think the more interesting sort of like large scale ML way of doing this would be to say like you'd want to, like, again, like these are sort of heuristics that we use because these are decision scales by focusing on the Western US and so on. But as such, and I think there have been several papers since that I've really liked where they treat the whole globe as like, okay, these are all the fire occurrences, and then depending on the weather patterns, you do the clustering on the whole globe, and then you build a model on like several of these clusters together. So in some sense, like a more radical way of sort of training a model that works across regions is you would train it on different regions, right? Or like you leave some parameters free, and then you fine tune on different regions. Depending on these similarity scores, and see if the model works better. So there's the one one shot kind of thing, like train this model on the Western US and see if it works for Australia. And then there's the software approach where you identify similar enough years between these two regions, add additional data, and then leave out different parts of these two regions which are not in the training data set, so which you've not considered, and then test the model on those. So for instance, you would just keep California and Victoria in Australia, and then test it on like Northern Australia and Washington State. That could be one of these hybrid sort of tests that you could do. I mean, I have no intuition of which one will work better. I think this is like a direction that could be explored. It's just, this is beyond the scope of what I was doing.
Yeah, thank you. That's interesting.